Okay, so the second to last speaker of this afternoon is Caio Melo, who is also a PhD student here at IMPA, and who will talk about transversely projective structures on smooth foliation on surface.
So I'd like to thank the organizers. Happy birthday to Fernando. And today I'll talk about the transversely projective structures for smooth foliations. And it was a notion that it was introduced by Barbosa on Tuesday, but he talked about the singular notion. And I'll talk about the smooth notion of this structure. So this began with the work of Bivas and Dumitrescu just this year, where they show that in the product of two elliptic curves, a generic turbulent foliation does not limit this structure. And so the question raises, under what conditions does a smooth holomorphic foliation on a surface admit this smooth transversely projective structure? So I'll begin with the definition. So for me, holomorphic or smooth transversely projective structure is a collection of submersions for your foliation. And so normally you define a smooth foliation by submersions to C, a codimension one foliation. So now I'm doing to P1, the projection line. And the transition functions are just Mobius transformations. Something interesting is when the space has dimension 1, and so one recovers the definition of projective structure for curves. And in the case of curves, there is always a smooth projective structure. So we'll talk about this here. So I'll call canonical projective structure for curves. And this is basically by taking the universal covering of your curve, and since this is simply connected by the Riemann uniformization theorem, this has inclusion to P1. And by taking local sections here, you can construct your canonical projective structure. This will be useful for us. So associated to this structure, we have the monodromy representation, which is basically taking those transition functions around a loop, which is a very important tool for our work. And why smooth foliation? Because we have the smooth foliation on surface, because we have the classification of Brunella. And by classification, we have this list, and so Bivas and Dumitrescu shows that the generic turbulent foliation does not admit this structure, and what we did was to show when these two cases in fact admit this structure. The other three cases always admits, and I'll talk today about the first case when we have a foliation given by a fibration. So we'll talk about fibration. So what will be a fibration for me? It's a proper surjective map to a complex curve, which I'll probably assume to be compact, and I'll mostly assume to be compact. And it will be called smooth if the fibers are smooth, reducible, reduced divisors. I mean, there are no multiple fibers. And in this case, the foliation always admits transversely projective structure, because we can use this draw. So you take the foliation given by a fibration like this, and so you compose with these local sections, and you obtain exactly these submersions. And so what happens when we have multiple fibers? So this is the definition. I'll call, when we have multiple fibers, I'll say that the fibration is quasi-smooth because the fibers are smooth, but we are allowed to have multiple fibers. And associated to this notion, we have the notion of orbifold base, which is a way to encode this multiplicity on the base. For me, an orbifold will be just a curve. It will be an orb curve. And if we have a fibration F, then we can construct a divisor. So an orbifold will be a curve and a positive rational divisor, giving multiplicity to those points. And we have the notion of good and bad orbifold. A good orbifold for me will be an orbifold which has an unfolding, which is a triple of a curve, a discrete group acting in this curve, and the projection gets your base back, your initial curve, with a ramification divisor being the pullback of your delta, which is the divisor I defined before. And when this doesn't happen, we have the notion of bad orbifold. Thanks to Bungard, Nilsson, Fox, we have the bad orbifold is a simple case. So it must be P1 with only one multiple point, or P1 with two multiple points. And why bad orbifold? So in the case of fibration, this is exactly the case. The good orbifold is exactly the case when the induced foliation admits a good smooth transversely projected structure. And a counter example of this, an example to illustrate this is the foliation on a Hopf surface, where we take the quotient map by Z like this, and we consider the quasi-smooth fibration given by this. And so the orbifold base will be like the first case, the theorem, and because of the proposition, it's not, the foliation induced is not transversely projected. Okay, so the proof of the proposition, so we first assume that the foliation admits this structure, and we apply Selberg lemma to construct a fine subgroup of the fundamental group of X, where the image by the monodromy I told is torsion-free. And we take the covering with respect to this group, and the pullback will be given by a smooth fibration because the image, because of this condition of torsion-free. And since G, the group of deck transformations, will act on C, so the quotient will be our base B. And this will induce an unfolding for the orbifold we started, which is the orbifold base of the fibration. Okay. So now, if we begin with an orbifold, so if your orbifold is good, then if we begin with an unfolding, then we take the normalization of the fiber product, and we have like, so now we have like something like this. And here is F, here is, yeah. And so the pullback of the foliation given by this fibration will be given by this smooth fibration. And one can show that this will have a transversely projected structure by what I said, and this transversely projected structure will be invariant by the group G acting on X tilde, and so we can descend this structure for the space we began. So our theorem uses this proposition because we show that for a compact Kähler surface, a quasi-smooth fibration has a good optical base. So by this proposition, the foliation will have a smooth transversely projective structure. And by basically analyzing the proof of the proposition, we see that after italic covering, the fibration becomes a smooth fibration, which is exactly this one. And so I will show you the proof. So, okay. I will suppose for simplicity that the obfold base is P1 with just one point of multiplicity. And so I will show you, I'll give you. And since it is a multiple point, so we can apply Hib local stability theorem to see that a local leaf, a leaf around here, L, is a covering of this multiple leaf. And since we have a covering, we can take a deck transformation. And so we'll take a deck transformation, a non-trivial deck transformation, and consider the Lefschetz fixed point theorem. Since it has no fixed point, so one part of this equation must be 0. And I'll try to simplify the other parts of this equation. And I will do this by considering the local system given by a higher direct image over the complement of delta. So, okay. So this local system is the local system associated to the press sheaf that takes U to a U open set of the base to the cohomology in the pre-image. And so we have associated this monodromy representation. And notice that since we take B and delta to being P1 with just one point, then the complement of delta is simply connected. And so this monodromy must be trivial. And from a local argument, we see that the deck transformation G we started is given by an image of this monodromy. We see this by, so locally, this map is like this. So we have an open set here, a disk that goes to a disk. We have the fibration here. Locally, here in the base, we have a branch covering given by the powers of n. And here we have a respect covering, where here we have an action of z over nz. And this leaf, now, after passing to this covering, becomes n separate leaves. And what is our map G? So G is basically taking one of these leaves and going to another. It's permutating those leaves. And this will corresponds to a path, a not closed path down here, where when we go back to our initial base, it will become a loop. And when we see the corresponding deck transformation, it's exactly RG. Okay. And so since the monodromy is trivial, the pullback map for this G is always trivial. And since the pullback is trivial, the map inducing the homology must be trivial. And so we can simplify the equation for Lefschetz. Basically, it's the Euler characteristic, topological Euler characteristic. And since it's 0 and L is a curve, it must be elliptic curves. I'll use this later. Before that, just notice that if we take here I being 1, for I equal to 1, and using that it is trivial, we conclude that, so we have this theorem of Delign's invariant space theorem that states that if iota is the inclusion, then the image for the pullback in the first homology is it's the subspace of the cohomology on the fiber that is invariant by the monodromy I told before, and which is a trivial monodromy. And because of that, the pullback morphisms must be surjective, and so we can extend every one form on L. Oh, I forgot to mention, but this induce also morphisms on the Hodge decomposition. And again, it will be surjective. And so now we are using that L is elliptic to construct one form that doesn't vanish on L, and we can extend this one form to the whole space. So this one form will induce a foliation because we are on a surface. So omega induce the G foliation, and it will be transversal to the, and G is completely transversal to F. And why is that? So because we see that if you take the integral of omega, wedge the conjugate of omega, then this is more than 0. This is not 0 because it's a nowhere vanishing, as I told. And if we take another generic fiber, this must be equal. Oh yeah, I forgot to mention, but this is simply omega L. And since the LP, which is our multiple fiber, is covering by the rib, is covered by L, by the rib local stability theorem, this is something like 1 over n LP omega wedge omega bar. And so all of this is not 0. And so the G must be trivial, it must be transversal to our foliation F. And okay, and so by Aboville's theorem, this implies that we have a split of our tangent space, tangent sheaf, and so the covering of our X, the universal covering, must decompose on the product of simply connected curves, and the pullback will be the projection on one of these curves. And this will induce an unfolding for our fold base, which is a contradiction, as I told, to being a bad unfold. So this proves the dimension 2 case, the case of the surface. And for dimension 3, we were able only to prove for a projective manifold, where we applied the foliated MMP program, foliated MMP for codemission 1 foliation on threefold, a work by Count Spicer. And here we are using the fact that it is smooth, again, and the foliation is smooth. And so we analyze the possible cases, and we conclude some arguments repeats on one of those cases. And so again, we have the corollary that after passing to an ETL covering, the foliation is given by smooth vibration. And yeah, that's it.
Are there questions or comments?
So you're doing something like Picard-Lefschetz theory for in this situation, no? Is this something that is known in general, this is, for foliations, or you're just doing it for this case? Or is there already developed such a theory in general? Do you understand that?
So when we start working on this, we looked for reference. There are results that are similar. So there are results by that. I think it starts with Beauville, saying that vibrations on surface of general type had at least 3 singularities as soon as they are non-isotrivial, and there are higher dimensional versions of that. But amazingly, this simple observation we couldn't find in the literature. And it's funny because it does not work if you are outside the Keller world, because you have this example with hop surfaces. But in the Keller world, this simple argument seems to take care of it up to dimension 2. Dimension 3, we need a bit of technology. And we are wondering if we do have technology to do in general, but we don't know. We don't know if it should be true. I don't see any reason for not being true. It's a very simple question, but doesn't seem to be treated in the literature.
Yeah, exactly.
Any other question? Callum will give a proof in dimension 4.
So for codimension 1 foliation, that's the case for B is dimension 1. What about if B is dimension 2? Are you able to get any interesting statements?
Sorry?
So if you have a vibration over from a threefold to a surface,
Oh, okay.
do you have
B has
any
dimension
interesting
2.
statements there?
Yeah. So, yeah, I didn't think in this case yet. Yeah, so we don't have we lose this proposition that where we can use an orb fold. Right? We have to use more general notions of orb fold.
Forget about transversely projective structure. We're talking about vibration. Your talk was about vibration.
Yeah.
You had this transversal or whatever, but you can forget about it and think only about vibration. Vibration by curves over a surface. That's what he's asking.
Mm-hmm. Yeah, one can think of can define smooth foliations given by vibrations like this. Yeah, yeah. And, yeah, I think I don't think I understand the question.
Oh, I mean, I guess the last thing we said. I mean, I guess is there anything you can say along these lines, like in the rest of your theorems? Is there any analog for three-folds fiber over surfaces?
Yeah, I don't know.
Any further questions or comments? So I think we are a bit let's see. When is the next talk supposed to begin? And 5:20, but I think we can, since it's late, we can start at 5:15, so we start 5 minutes earlier, and it will be the last talk of the day by Pablo. And so let's thank Caio again.